and I say that at the beginning of all my streams. All right. So here is the problem that we're going to be doing today. So the scenario is I have a 200 kilogram refrigerator, and I want to figure out what the coefficient of static friction is when I'm applying applying a force to the refrigerator. Okay. So what we're going to do is we're going to start applying a force to the refrigerator, and we're going to try to figure out what the maximum amount of force that I can apply to the refrigerator before it begins to move. Because that would be the instant it switches from static friction to kinetic friction. All right. Or friction of being stationary to friction of motion. So what I'm going to do is I'm going to increase the amount of force that I'm applying. Now, while I'm doing this, I want you guys to notice what happens to the frictional force. Yes, I am on YouTube Live. So if you guys go to that link I just sent in that last link, you can see it live on there. So if you guys have your phone, you can have it up watching that, and then you can be taking notes. Okay, so when it comes to static friction, watch the behavior as I increase the force. So I initially had 0. Of course, there's no force present. There's no friction force. I apply 1 Newton friction force. The static friction force is 1 Newton. I apply 2. The friction force static. The static frictional force is 2. This pattern is going to continue until I reach that threshold where it breaks free from the surface and starts to slide. Okay? So as I'm increasing the applied force, the frictional force due to static friction is going to negate my applied force at the same rate. Okay? So if I apply 52 newtons, it's going to push back with 52 newtons. If I go up to 102, it's going to push back at 102. Is everybody tracking? So the maximum that I can apply, I did this in my last class, so I know exactly where it's at. So the maximum amount of force that I can apply to the refrigerator without it starting to move is going to be 220 newtons. If I apply even just a tiny bit more force, it will then break free because I've now breached that threshold, and the type of friction will go from static and it'll convert into kinetic. Okay? So when that happens, I want you guys to watch this red arrow here. Watch the number. And somebody tell me what happened. When I add 1 more Newton, so when I go up to 221, I switch from static friction into kinetic friction. So I'm going to do that now. What happened to my frictional force? It was 220. Now it's 165. So remember, just a second ago, I was applying, wait for it to stop. I was applying 200. So would you guys agree that right now it's not moving? Right? So that's because I have not yet breached that threshold. I have not broken free from the surface. I have not done that switch from static to kinetic. But once I do, I can push really hard to break it free. So I'm going to go to 250 real quick. It starts to move. Now I'm going to go back to 200. And look at that. It's moving, but more importantly, what's happening to my speed? It's increasing. So that means that if my speed is increasing, if I'm changing my state of motion, I'm going faster and faster as time goes on. I'm at 4.5. Now I'm at 5. I'm at 5.5. And it's speeding up, right? So that means that there is a net force my forces are not balanced if my speed is changing. So even though I was initially at 200 newtons, once I went to 250 and then went back to 200, I now have enough net force to start increasing my speed. Make sense? So I also want you guys to take note. Watch what happens, because before, as I was increasing the applied force, my friction force was doing the same thing, right? I was at 0, then I went to 50, then 100, and the friction force was matching it, right? It was doing the same thing, it was copying. But once I'm in the kinetic friction, once I have kinetic friction present, watch what happens to my frictional force. I'm going to hit play, and as I increase my applied force, what's happening to my frictional force? It's not changing. I can go and just keep going up and up and up. Nothing's changing with my friction force. So what would happen if I just stopped? What if I just turned it off? Friction force still didn't change. Friction's still present. So this is the friction due to motion. Okay, this is this is the, how do I want to say this? The force due to kinetic friction is the force that stops things from moving. It brings things to rest, which it just did. All right. So kinetic friction takes something that's moving and makes it stop. Static friction, on the other hand, takes something that's already stopped and keeps it stopped. All right. It keeps things at rest. That's what static friction does. Static friction keeps things at rest. Kinetic friction takes something that's already moving and makes it go to rest, or tries to make it go to rest. It tries to oppose motion. That's the biggest difference between the two. In the video that I posted on Edpuzzle, you'll notice that when it comes to static friction, the value will change. The force due to static friction will match what my applied force is, but just in the opposite direction. But it doesn't matter. Once it starts moving, the force due to kinetic friction will remain the same as long as the object is moving. Okay? So that's another key point there. Hint, hint, might be a question about that on the video. Okay, so now that we all understand the process, I want to know what the coefficient of static friction is for this scenario. So we know that the threshold was at 220 newtons. So 220, that's the maximum amount of force that I can apply before it breaks free. Cool. So, didn't mean to hit the mic, I'm sorry. So here is our situation. We have, apologize. So we've got our refrigerator right here. And this refrigerator is made out of matter. Matter has mass, and we are on Earth, right? So if we have matter and it is subjected to a gravitational field, gravity, then we're going to have something called the force due to gravity, or what we call in everyday speak, weight. So we have the force due to gravity, and what direction is that going? Up, down, left, right, circles. In this case, it'll be pointing down, okay? Because this is a horizontal surface. This is the ground. Force due to gravity is going to be pulling it to the center of the Earth. So this is representing force due to gravity, F sub g. And just as a side note, force due to gravity is equal to whatever the mass is multiplied by the acceleration due to gravity. So since we have force due to gravity here, we can go ahead and put this equation, force due to gravity is equal to mass times gravity. Now, we can observe that in this scenario, the fridge is not sinking into the ground, nor is it floating into the air, right? So that means that if it's not changing its state of motion, it's currently at rest at a certain height in the ground, it's on the ground. But if it's not going up and it's not going down, don't we need to know how much gravity Earth has? Yes, I'll get that in just a second. You're going to have an aha moment and be like, oh yeah, forgot about that. But I'll touch on that in a second. So what I want to explain is we know that the force due to gravity is pulling down, but I know that in order for something to remain at rest, there has to be something that's preventing it from moving. So if gravity is pulling down, what's keeping it from being sucked into the earth? Anybody? What's counteracting the force due to gravity? So just like we mentioned last time, or I don't know if it was last time or not. So what's keeping, like if I set a book on a table, what's preventing the book from hitting the ground? So if I've got the ground there and I've got like a little table like this, and then I'll put a box on the table. All right, we're assuming that it's on the table. What's keeping the box from hitting the ground? Don't think too hard. What's getting in the way? All right, Liza, you're okay. You guys are thinking too hard. What's getting in the way? The table, right? The table is preventing it from touching the ground. So the table is actually pushing back like that because gravity is trying to pull that box downwards. So this is the box and it's trying to go down, right? But the table is getting in the way. So the table is going to be pushing back on the box the same way, right? The same amount. Is everybody tracking? So this is where that video on Edpuzzle about the normal force will come into play. So for those of you who are kind of getting confused, I would highly recommend watching those videos after we end class today. Okay, specifically the one about normal force. So the normal force is just the force of a surface pushing back on an object. Okay, so do you guys remember the example of when I had the cardboard box pushed up against the wall? I think we did it a couple of days ago. Yeah, right here. I was pushing the box into the wall and the wall was pushing back on me. And then before that, we were talking about that. Normal force. That ringing a bell? It's not? Okay. Interesting. All right. So I would recommend looking at the videos on Edpuzzle. That should clear up a lot of questions. So if I have an object that's making contact with the surface, that surface is going to prevent the object from morphing into it, all right, or sinking into it. It's going to push back, right? So we know that whatever number force due to gravity is, the normal force is going to be the same number, but just the opposite sign. So if I've got 5 for the normal force, that means that the force due to gravity is going to be 5, but it's going to be a -5 because it's going to be the same value, same magnitude, but just opposite in direction. Make sense? Same value, same magnitude, just opposite directions. So just like this. If an object is at rest, and I know that there's a force being applied, all right, so In this case, we wouldn't know the value of force due to friction if it was in real life. I would know how much force I'm applying, but we would have to figure out what the force due to friction is, like this force. And the reason why we can conclude that it is the same is because my object is initially at rest, and once I apply a force, it's not moving, it's not changing its state of motion. But sorry, Anthony just came in. Let me get him real quick. I apologize. So I know that even though I'm applying a force, the object's still not changing its state of motion, so there must be an equal but opposite force canceling mine out. If I'm applying a force and it's not changing its state of motion, my net force, the overall force, is 0. And that's what we can see here. The sum of the forces is equal to 0. Cool? So if I know the force due to gravity must be present, and I know the refrigerator isn't somehow where's my mouse? That it's somehow not sinking into the ground like this as time goes on, then I know there must be an equal but opposite force keeping it from doing that. Cool? All right. So what that means is, in the y-axis, so my net force in the y-axis, remember net force is just when I add up all the forces in the y-axis, I know it is 0 because it's not moving, or it's not changing its state of motion in the y-axis. So I know that it's 0, and because it's 0, I know that if I add my normal force to my force to gravity, if I add those two together, if I sum them, it must equal 0. So I'm going to have the normal force plus the force to gravity, and that's going to equal 0. Is that clear? Is everybody caught up? Can I get some feedback? Okay. All right. I know that these are equal in magnitude but opposite in directions, and that's how I got this. Now, in the y-axis, in the x-axis, this one's a little bit easier now because we actually can see the arrows. So there are two forces acting in the x-axis. We have the force applied, or the pushing force push, and we have the frictional force. So obviously right now in the simulation, it's not moving, but I am applying a force. So if I'm applying a force, there must be some other force present to cancel mine out. Because if it's at rest and I'm applying a force, it should be moving. But because it's not, there's something present that's canceling my force out. So what we're going to do is we're going to represent the pushing force going to the right. So this is force push. And then the frictional force, we will draw in the opposite direction. And technically all these arrows in the x-axis and the y-axis should be equal in magnitude. But we're just going to assume they are. So the force due to friction, static, is going to be pointing to the left. Cool. So just like I did with the y-axis, the sum of the forces in the x-axis must also equal 0, because we can observe that I have not paused it. This is like time is going on right now. I'm applying 220 to the right. Friction is applying 220 to the left. The sum of my forces is 0. So therefore, the state of motion is not going to change. So all the forces that are in the x-axis, I have force push plus the force due to friction, force due to static friction, sorry. Okay. And then from last class, when we were actually talking about friction, I gave you guys the equations for force due to static and kinetic friction. So since we're obviously dealing with friction here, I'm going to go ahead and write down that equation. So since we're dealing with static friction, so the force due to static friction is just going to be mu sub s, which is the coefficient of static friction, which is what we're looking for, multiplied by the normal force. Okay? So, oh, Cameron, there ain't no SOL, bud. You think I would teach a class with an SOL? You crazy. So on an assessment, you guys are allowed to use equations. Okay. So I'm showing you guys where these equations are coming from. But I will tell you which ones to write down. The way that I'm going to be doing this and the way that I'm running my class, because we're virtual, I'm going to be doing the algebra. Okay. So if you guys follow along, you can figure out like where these equations come from. But if the algebra is too confusing, just keep watching, and I will box the equation that you need to write down. Cool? If the algebra confuses you and you're good with the concepts and all that kind of jazz, you can figure out what the knowns and the finds are. Don't worry about the algebra part, because I'm not here to grade you on your algebra. Okay. So let's kind of get through this quickly. And again, this is being live streamed, so you guys can go back and watch it. All right. So my goal for this problem is to figure out what the coefficient of static friction is. Now remember, the coefficient of friction is letting us know how frictiony a surface is. You know, if something's really smooth, it's going to have a low coefficient of friction. If it's very rough and bumpy, it's going to have a high coefficient of friction. And the video on friction will help reinforce those concepts. Now, we have to keep in mind that the coefficient of friction, scroll up real quick. So the coefficient of friction is represented by the symbol mu, and it's always going to be greater than 0, but also less than 1. Okay, so if we get a value at the end and it is lower than 0, i.e. negative, which usually won't be the case, more often the case, you're going to get a value, if you do it incorrectly, you're going to get a value that's greater than 1. So you have like 1 point something like your math is wrong, or something, you didn't plug something in right. It's always going to be 0 point something. Okay. It may not have 2 digits. It might just have 1, but it's always going to be 0 point something. Cool. All right. So we want to find mu sub s. All right. So the very first thing that we do, so this is my find, mu sub s is equal to something. What do we know? So in this problem, we know 2 things. All right, we're going to pretend that we don't know what the value for friction force is. Okay, so we're gonna block that out. Cool. Because in a problem that I give you as like a problem for a quiz or a test, I will not give you the value for the friction force. I will give you the applied force. Cool. And it's not going to make it any more difficult, because at the end, I'm going to show you the equation that all you're going to need for this problem is the applied force, the mass, and then the acceleration due to gravity. That's all you need. And it's going to be arranged in a certain way that you'll see at the end. Okay. So I am given that the applied force, so force push, is equal to 220 newtons. It's a weird looking N. So 220 newtons. I also know that the mass is 200 kilograms. So that's going to be M equals 200 kilograms. And since we know that we're dealing with gravity, I think Cameron... Yeah, so Cameron asked this question. He said, wait, don't we need to know how much gravity Earth has to get that answer? In other words, he's asking, don't we need to know gravity? So little g is the acceleration due to gravity. And in my class, just to keep the math simple, I use 10 meters over seconds squared. So the units for that make it an acceleration, and it's technically 9.81, but we want to keep the math easy. I want to make sure you guys understand the concepts. Okay. Now, this is where the algebra comes in. Okay, so this may be confusing for a little bit, just for a couple minutes, but I'm going to go through it pretty quick. Okay, so don't tune me out. Just keep watching. Okay, once I get down to the final thing where it's mu sub s equals something, and I box it, that's what you write down. That's the most important thing. Okay. So my objective is I want to find mu sub s. Okay, that is the coefficient of static friction. If I look at these equations that I wrote down a second ago, this equation you should have in your notes, and this equation you should have in your notes. Okay, these are very basic equations. But these two I got from the diagram. Okay, and they're very simple. This one is just adding up all the stuff that's in the y-axis, and I know that it's equal to 0 because it's not changing its state of motion in the y-axis. And the same thing for the x-axis. Okay, so which one of these equations, 1, 2, 3, or 4, has mu sub s in that equation? Let's be this one here. Equation number 4. So what I'm going to do is I'm going to write that down, and let's do this down here. So the force due to static friction is equal to mu sub s times the normal force. Okay. The variable that I want is here. So I'm going to keep that there, and I'm going to move everything that's on the side of the thing that I want. I'm going to move it over to the other side. So since it's mu sub s times normal force, I divide by normal force. So it cancels on this side. And if I do something on the right, I must do it on the left. So what this gives us is mu sub s is now equal to the force due to static friction over my normal force. And again, if I'm going too fast, this is recorded. All right. So my first goal is to get what I want, the variable that I want, on the left side. This is what I want. It is on the left side. So I get a check mark. So that's good. Now, let's see if I can plug anything in. Do I know the force due to static friction? Is that given? I'll look over here at my knowns. No, it is not. So can't use that. Am I given the normal force? Nope. So that's a big old negative right there. Okay. Now, when we run into these situations, we don't just call it quits because we're like, oh no, I don't know friction force. I don't know normal force. Let's figure out if we have something that we can substitute in. Let's start off with the friction force. So since we've already used this equation here, we can't use it anymore. So that one's used up. So where is force due to static friction? Is it in here? Nope. Is it in here? Nope. Oh, look at that, right here. So this is the force due to static friction. And what I know is that the force due to static friction is equal to, oops. It's the force due to static friction plus force push equals 0. Right? So putting the equal sign on the left or the right doesn't change anything. So I want to get rid of, or I want to solve this for the force due to static friction. So if I have that plus, oops, that was weird. This is added to this. In order to get this out of there, what do I have to do? I have to subtract. So if I subtract it on this side, it cancels out. And then I get minus F push. So we already knew this logically, but this is just the algebraic way of explaining it. So the force due to static friction is going to be the same number as force push. They're going to be the same, but they're just going to be opposite in sign. Make sense? So instead of having force put or force due to static friction right here, we're going to swap that out for force push, but just the negative of force push from here. So all I did was I just substituted it in. I'm going to do the same thing for normal force because I'm not given normal force. So since we just used the x-axis, we can't use that again. So this is where the normal force is at. And I'm not going to confuse you guys with any more algebra. So the normal force, cannot make my ends right today, is just going to be the opposite of the force due to gravity. Cool. So that's what I'm going to do. I'm going to substitute in, my goodness, like that. So normal force is equal to the negative of force due to gravity. So if I've got negative on top of negative, what happens to the negative signs? Negative signs cancel out. So we have force push over force due to gravity. So let's see if we can plug in values now. Do we have force push? We have force push, so that gets a check. Do we have force due to gravity? No, we do not. So that gets an X. This is the last algebraic step. So since I already have force push, I'm going to just copy that one down. Now, I'm going to go back up to my equations. We've now used all but one, and we have force due to gravity now. So force due to gravity, I can substitute in mass times gravity, or mass times the acceleration due to gravity. So instead of force due to gravity, that's going to be now mass times the acceleration due to gravity. And we know force push is present. Do we have mass? Yep. And do we have acceleration due to gravity? Yep. So we now have check marks all across the board. And this, my little students, is the final equation. So if all that algebra was kind of mind-blowing, I apologize. But I was trying to go through it quickly so you guys can see the final equation. This is the one that I was saying that you should write down. So, that being the case, let us plug in what the values are. So whenever I plug in values, it's a very good habit for wherever your variable is to put open, or I should say empty parentheses, so you get the order correct. So the value for force push was 220 newtons. The mass was 200. And the acceleration due to gravity in Mr. Applewhite's class, to make the arithmetic easy, I want to make it 10. So those are all values that are present in our knowns box. Cool. So what we end up getting when we actually calculate this, we get 220 over 2,000. And that simplifies down to 0.11. And that is the final answer. Now remember, the coefficients of friction do not have units. So to kind of prove that to you, the units of force are newtons. In the bottom down here, we had kilograms for the mass, and then we had meters over seconds squared. And we know from a while ago that a kilogram times a meter over seconds squared is equal to a newton. So that means I've got a newton over a newton. So that will cancel out. So there are no units. But you guys don't really have to worry about that, because the way that I set these up for you is if you use the equations that I give you, the units will come out properly. Okay, I'm not going to make it so you guys have to do any kind of unit conversions or go from kilometers or any of that kind of stuff. I'm going to give you the proper units to work with, and then you just have to put them in the right spot. Cool. So, are there any questions? So just to recap, I know it was a lot. And then we finally used this last equation. So we had an example where we were pushing a refrigerator that had a mass of 200 kilograms. We applied a force of 220 newtons. And what the objective was to find out the coefficient of static friction. We drew out the diagram representing all the forces that are acting on it. We recognized that the forces in the X and the Y axis, the sum of the forces, the net force in the X axis was 0. So when they added up, the sum was 0. So that's how we got that. And we just added the two forces that were present in the X axis. And we did the same process with the Y axis to get this equation. We know that it's not changing its state of motion vertically. So we know that the net force must be equal to 0. And then all we did was we just added up all the forces that are in the Y axis. So that's how we got these two. Because we're dealing with force due to gravity, the weight, I apologize about the dog, we knew that from our equation sheet. And if you haven't written that one down, I would definitely recommend doing that. It's very commonly used equation. And then since we're dealing with friction, and we're more specifically dealing with static friction, this equation should also be on your formula sheet. Cool. And then we went through the process of solving these four equations and manipulating it so that we have mu sub s on one side, and we only had things on the right side that we have in our knowns box. And you don't have to worry about any of the algebra. This here, if I give you a problem just like this on, say, a quiz or an assessment, and I ask you to solve for mu sub s, you don't have to do any of the algebra. This equation here that I have the arrows pointing to, this is the equation you need. I've already done the algebra. Why do it again? I'm going to give you force push. I'm going to give you the mass. I may not necessarily give you acceleration due to gravity, but since that's one that we use a lot, that's something that you should know. It's very easy. G equals 10. I don't ask a lot from you guys, but I think you can get that. So the two pieces of information that I will give you, no question, would be force push and the mass. And you should be able to figure out what the coefficient of static friction is from those two pieces of information, assuming you remember acceleration due to gravity. Cool. So I'm hoping that this lesson went okay. I apologize if it was going too fast, but that's why I have it live streaming. And I'm going to